Can you think of a polynomial that can give any positive integer as output? One example will be this polynomial. This might look familiar. Yes, it's the four-square theorem, which says that any positive integer can be written as a sum of four squares. But what about something like this or this? Is there a simple way to verify the fact that these polynomials can represent any positive integer? Well, it turns out that if the polynomial takes all the values from 1 to 15, it will inevitably represent all the positive integers. The surprising fact follows from what is known as the 15 theorem. The theorem states that if a positive definite quadratic form having integer matrix represents every positive integer up to 15, then it represents every positive integer. A quadratic form is simply a polynomial where every term is of degree 2. A positive definite quadratic form is a quadratic form which outputs a positive result for every non-zero input. Finally, an equivalent matrix for the form is the one which satisfies the following property. Here consider X as a vector. For example, consider this quadratic form. The equivalent matrix will be this. Let's cross-check. Upon computing the product, we have the original form. This theorem was first proven by John H. Conway and W. A. Schneuberger. Interestingly, the proof was never published, probably because it was too complicated. Fortunately, Manjul Bhargava found a much simpler proof in the year 2000, and I promise to cover the proof in a future video, but for now I will just provide the resources in the description. A similar theorem was also stated by Conway, known as the 290 theorem, which states that if a positive definite quadratic form with integer coefficients represents all the numbers from 1 to 290, a more precise version states these 29 numbers, then it represents all positive integers. This theorem as well was proven by Manjul Bhargava along with Jonathan Hanke, which got published in 2005. That's it for today's video, and I promise to upload a video featuring the proof of the 15th theorem.